Okay, so can we run through some of this? Ryan, can you start us off with the definition of KC, please?
Equilibrium constant is the constant for a given reaction at a given temperature.
Sorry. I shouldn't have written KC definition, should I? I should have written KC expression. That's what I should have done there. What's the expression for KC? Remember that important word expression always means maths. What's the expression for KC for this reaction?
Is it products over reactants?
It is? Give me a bit more.
At a given temperature.
Hey?
At a given temperature.
Yeah, we'll come back to that. I want the mathematical expression for KC for this reaction.
Is it moles? Decimeter cube?
No, you're thinking about units. Just want the expression based on that.
Oh, is it x and y over?
Yeah, except we don't have X and Y. We've got CO, H2 and CH3OH.
So CH303 over.
CH3OH.
Yeah.
Okay. What about the CH3OH? What property of it are we measuring?
Concentration.
And how do I show concentration in the expression for KC?
Moles. Oh no.
How do I show it?
The square brackets.
Square brackets. Good. Now we're getting somewhere. So square brackets around CH3OH means concentration of methanol over.
CO and H2 to half.
Yeah. So the square brackets bit we just pronounce as concentration of. So concentration of CO times concentration of H2 squared. Okay. Right. Thank you for bearing with me there. Right. The effect on the equilibrium yield of methanol when the temperature increases. Shall I take a go at this? No problem?
The yield would decrease as it shifts as the equilibrium shifts to the left in the endothermic direction in order to reduce the excess energy. Shifting to the left would increase reactants and decrease products.
Okay, you covered it all there. You didn't actually need the extra bit at the end. You'd already nailed it. So notice that he referred to the equilibrium yield. It's not enough just to say it shifts to the left. You've got to say it shifts to decrease the yield of methanol. And then, I can't remember how you phrased it. You said
Shifts to the left in the endothermic direction.
okay, so shift to the left in the endothermic direction. So it's exothermic forwards, so endothermic backwards. So shift to the left in the endothermic direction, decreasing the amount of methanol. And then Le Chatelier at the end was?
To reduce the excess energy.
To reduce the extra energy. Lovely. Okay, that Le Chatelier statement is really important. Eh? Yeah, so be 3 marks for this question. So what's the effect on equilibrium yield of methanol? Well, the yield would decrease. Why? So the principle, when temperature increases, equilibrium shifts in the endothermic direction. Shifts the equilibrium in the just remind the examiner that you know which that is. So you might say, which is to the left, or which is backwards, or the reverse reaction. And then the last bit is the Le Chatelier statement. We're saying this happens because Le Chatelier's principle that for change in the equilibrium, change in the conditions for a system in a state dynamic equilibrium, the equilibrium position will shift in the direction which minimises the change. That's what we take into the exam. to minimise the change, well, we've increased the temperature, so the reaction goes endothermic to reduce the temperature, to absorb that energy. That would be a good word there, to absorb that extra energy. All good? All good. Okay. Can we skip to number 4? I should have done these in a different order, but that occurred to me afterwards. How does that affect KC? Go for it, Jamie.
KC will decrease as
KC.
reactions exothermic.
KC decreases. Yeah, as you said, reactions exothermic, but we know from our work here, the equilibrium shifting that away, making less methanol, more of that, that's going down, those are going up. That means that number, that fraction will get smaller. So Kc will decrease. Okay, good enough? Could somebody talk us through the effects of equilibrium yield for ethanol and pressures increase? Someone else? Do that for us?
I said equilibrium yield will increase as an increase in pressure because of the shift to the right to reduce the pressure.
Okay, so we've got yield increases, tick. Equilibrium shifts to the right. So there's two things we have to say. Why to the right? And
Because there's less mole.
okay, so fewer moles of gas on the right. Okay, yeah, that's grand. Fewer moles of gas on the right, so we're shifting to the right because in Le Chatelier terms that will.
Minimise the change.
But we're not going to say that. You're going to take that into the exam in your head, and you're going to say,
It'll lower the energy change.
what have we changed?
The pressure.
So what's shifting to the left? Sorry, shifting to the right going to
It's
do?
going to change it's going to reduce the increase in pressure.
Reduce the pressure, or yeah, stop that increase in pressure. Okay. How's that affect KC? Nothing. Great. No change. Because KC is only affected by temperature. Okay. Right. I want to do the last bit of teaching then. Which is nice baby. Actually set up the camera. Right, we're going to put some serious numbers into this subject. In GCSE, it's not very numeric, is it? We just sort of talk about equilibrium shifting to the left and shifting to the right, really put any numbers on it. But let's do this. Okay, I know that probably looks like quite a complicated reaction, but actually it's fairly simple because one of those reacts with, go away. One of those reacts with one of those to make one of those and one of those. A plus B makes C and D. There's no balancing numbers in it, which makes it a relatively easy example to start with. I realise the chemicals are probably not particularly familiar. You might have come across them in separates chemistry last year. But so we've got ethanol and we've got ethanoic acid on the left. And on the right, we've got this ester. I'm just going to call it the ester from now on rather than ethyl ethanoate. And then water is water. Okay. So ethanol and ethanoic acid makes an ester, and it's in an equilibrium with water as well. And what we can do, like experimentally, is leave the reaction going, just leave it at a constant temperature in the back corner of a lab somewhere until we're fairly sure it's reached equilibrium. And then we stop the reaction and we measure the concentrations of all the different things in there at that time. So we're going to start off by saying that we've got 1 mole of ethanol and 1 mole of ethanoic acid, and we're going to let them react for a bit. And then at equilibrium, when we come back an hour later after lunch, we've made 0.4 moles of ester. Okay, so far? Right. If I've got 0.4 moles of ester, how much ethanoic acid and ethanol will I have left?
1.6.
Sorry?
It might be 1.6.
Where'd you get 1.6
Because
from?
you add the 1 to the atomic 2.
Oh, we'll see. No, we're not going to add them together because they're separate reactants. We're going to treat them separately. So I need the amount of ethanol and the amount of ethanoic acid, 2 separate numbers.
0.6.
They'll both be 0.6. Okay, so we've got, this was initially, we had 1 mole of that and 1 mole of that and none of that and none of that. And then when we come back after lunch, we've got 0.4 moles of ester. How much water would we have? 0.4, yeah, because if I'm making one of those, I must be making one of those. Because they're in a 1-to-1 ratio. And if I'm using up 0.6 of that, I must be using up 0.6 of that, because they're in a 1-to-1 ratio. Okay, now, hopefully that's fairly straightforward and intuitive, but once we're going to add balancing numbers, things are going to get a bit harder. So what we do is we add a change line to our table.
I'm going to talk.
Of course you can. So our ester and our water have both gone up by 0.4, and our ethanol and our ethanoic acid have both gone down by 0.4. Okay, and that brings us up to there. Everyone with it so far? So this is why it's called an ice table. Okay, because we have that initial state, we have the equilibrium state, and between the two we have the change. Now the key thing to note is that ignoring the pluses and minuses, the changed numbers, 0.4, 0.4, 0.4, 0.4, are all in the same ratio as the balancing numbers, 1 to 1 to 1 to 1. I'm just going to say that again. Ignoring pluses and minuses, the numbers on the change line are in the same ratio as the balancing numbers. Okay, with it so far. Okay, right. What's the expression for Kc for this equilibrium? Could you write that down for me? Take it away. You're going to tell me?
I had ester in the bracket.
Yeah. So ester, concentration of the ester,
And then H2O.
concentration of water,
and then ethanol concentrate.
Concentration of ethanol, concentration of ethanoic acid. Okay, that's great, except these are not concentrations. These are moles. We measured moles. Doesn't actually say that, does it? But these are all measures of the direct measures of amount. Changes of moles. Okay, so we can't put those numbers straight into the equation. What is the relationship between moles and concentration? What would I need? Volume. So concentration is moles over volume. Okay, moles over volume in dm cubed. Just bear with me for a moment because we don't actually have a volume, but hey. So if I was to put this in, 0.4 moles, I would have to say 0.4 moles over a volume to make it a concentration. 0.4 over volume. And then for water, that would be the same. And then for these two on the bottom, well, that would be 0.6 over volume for ethanol and 0.6 over volume for ethanoic acid. What do you notice? In this case, yes, so therefore they cancel. In this case, the volumes cancel. Won't always be the case, sorry. But in this case, the volumes cancel. So we can get an answer, whatever that is. 44. What were the units for this KC? No, that's the units of concentration. What are the units of this KC? Remember, KC's units change. There will be nothing for this one. No units, rather than nothing, which sounds like you don't know what you're talking about. If an A-level question asks you what the units are and you say there are no units, that's pretty straightforward, isn't it? Okay. Right. So that was kind of a first example without any balancing numbers. You can bet that you're going to get some of those. So. What was that first equilibrium I gave at the beginning? CO and 2H2, wasn't it? So let's say we start off with 1.5 moles of carbon monoxide, and we'll start off with 2 moles of hydrogen. And as you normally in a reaction, you don't really start off with any product, do you? I mean, you might start off with some product, but let's assume that we don't. And at equilibrium, let's have 0.65 moles of methanol. Okay. So our first step is to fill out the rest of the ice table. So let's just walk through it. I'll give you a moment to get that all written down. Maybe think about which numbers in the ice table we can get to first. I'm just going to look at my watch for the time, please. 10 past. Magic.
11.
Plus 0.6.
Okay, so that's the easiest one to spot. To go from 0 to 0.65, that has gone up 0.65. Good. Okay. So our all-important change line, this middle one, remember, has to be in the same ratio as the balancing numbers in the equation. So if that's gone up by 0.65, methanol to CO, well, they're in a 1-to-1 ratio, so that must have gone down by 0.65. But what about the hydrogen?
Minus
Wrong way.
1.3.
That's 1.3.
We use up 2 hydrogens for every carbon monoxide we use up. So if I've used up 0.65 carbon monoxides, I must have used up 1.3 hydrogens. Okay. So we've now got 0.85 carbon monoxide, and we've got 0.7 hydrogen and 0.65 methanol. Okay. Now, volume's not going to cancel out in this one, so let's have a volume, and let's say our volume was 12 dm cubed. Okay. So our first thing we need to do is just write the expression for Kc for this equilibrium. Well, you did that already. You did that when we came in. Eventually, we got there. So the expression for Kc, the equilibrium constant for this equilibrium is.
Concentration
That's it.
of CH3OH over concentration of CO, concentration of H2 to the power 2.
Multiplied. Yeah, that's a multiplied by on the bottom. Great. Okay. So now what we're going to have to do is put some numbers in, and we're going to end up with a kind of big mess of numbers if we're not careful. Let's take it slowly. So methanol is 0.65 and the volume is 12. So on the top we've got 0.65 over 12 moles over volume in dm cubed. And on the bottom we've got CO 0.85 over 12, and hydrogen is 0.7 over 12, and then that all needs squaring. Okay. Hit your buttons, come up with an answer. Yeah, so if you number crunch that, 224.7 something, isn't it? So let's round it to 225 to 3 sig figs. That's the most accurate our data is. We need some units now.
The moles to the minus 3 dm to the power 9.
Mole per dm cubed on the top. We've got mole per dm cubed times mole per dm cubed squared on the bottom. How does that all cancel out?
More DM6.
Got to do the bits separately.
Oh.
Yeah. So we can cancel those for a start. So 1 over mole per dm cubed squared. If I kind of multiply that out,
Moles squared DM minus 6.
1 over moles squared dm minus 6,
Yeah.
and then
Mole.
get rid of the 1 over.
DM6.
Mole minus 2 dm plus 6. Okay.